In this video, I'm going to use SageMath to program partitions of a integer. So this video has nothing to do with abstract algebra necessarily. It's more a fun experience in terms of recursively programming the partition of an integer. Okay, so first of all, what are partitions? So the partitions of an integer n are the ways to write n as a sum of positive integers. And maybe what makes it a little difficult is that the order does not matter. So for example, 3 plus 1 is the same partition of 4, as 1 plus 3. And so the 5 partitions of 4 are 4, 3 plus 1, 2 plus 1 plus 1, 2 plus 2, and 1 plus 1 plus 1. So there's 5 of them. And again, 3 plus 1 is the same as 1 plus 3 as a partition. So we don't double count that. Okay. And so the partition function P of n counts the number of partitions of n. And so for example, P of 4 is 5. And there's no known closed form formula for P of n, although there are some recurrence relations formulas that can be used to calculate exactly what P of n is for an arbitrary positive integer n. And there's a lot of incredible or deep number theory and combinatorics that involves P of n. Some of it is due to Ramanujan. Okay, and according to Wikipedia, the function P of n grows exponentially, and P of 100 is approximately 200 million. So there's 200 million ways approximately to write 100 as a sum of positive integers. Okay, so here's the code I made for defining a function partition, which if you give it a positive integer n, it returns the list of partitions of n. So here's an example of, I've run this code. So partition of 4, it returns this list of partitions of 4. And if you want to find out how many partitions, you throw that list into the length function or len function, and what we get is this. Okay, so let's go through the code. And the main idea is that a partition of, say, 4 is, okay, it's either 4 or a partition of a smaller number added to a specific integer. So for example, if I have a partition of 4 is either like something like 1 plus a partition of 3, or 2 plus a partition of 2. And that's the main idea. So okay, so here's this recursive program defined to, I'm calling it partition. I don't know if SageMath has a built-in partition function. I tried looking quickly, but I couldn't find it. Anyway, so okay, if n is equal to 1, then just return the list containing the string of just 1, because the only partition of the integer 1 is just itself 1. Okay, then if n is not 1, then okay, let's cook up a list that's going to hold the partitions of n. That's what I eventually return. And so the first entry of this list is just the integer n itself. So in this case, when I call it partition of 4, it just returns, well, the first item is 4. That's the partition just consisting of that single number. Okay, and then we're going to add to that list these other partitions that involve not n, but numbers smaller than n. So the idea is that, okay, we range over the numbers from I, starting from 1 and ending at n minus 1. That's what the range 1 comma n does. And then you take a partition in partition of n minus I. So here we're recursively calling the partition function. This is kind of the fun part of this programming exercise in recursive programming. Okay, and so then for a partition of n minus I, you add to that partition P, you add the integer I. And so here's commented out here, is this the main idea, is that if you start with a partition of n minus I, then that partition plus I is a partition of n. And now I have this extra line, if I is less than or equal to int p of minus 1. Let's see what happens if I comment that out and then hit shift enter and then look at the partitions of 4. Now, if I don't have this line that I just commented out, when I run partitions of 4, it doesn't give me the right answer. And this is what I had first tried. So what's wrong? Well, it does give me, you know, a bunch of partitions, but then the order matters. You know, so 3 plus 1 and then 1 plus 3, for example, are considered different in this program, and that's not what we want. That's what makes partitions maybe a bit harder. Okay, so the problem is that the numbers in this partition, in these other partitions, 1 plus 3 and 1 plus 1 plus 2, they're not, and also I guess 1 plus 2 plus 1, they're not decreasing or strictly, sorry, I can't remember the term, but the main idea what I'm trying to say is that in the list here, the numbers are decreasing or stay the same. You know, when you go from 3 to 1, that's decreasing. 2 to 2, that's at least non-increasing, and so forth. Whereas here, in 1 plus 1 plus 2, there's an increase in going from 1 to 2, and so we don't want that. And similarly for 1 to 3. And so that's why we have to add in this line that you only want to add in the partition if the number you're adding is the number I, that's the number you're adding to your partition, is less than the partition less than the numbers in the partition of n minus I. And so I wanted to emphasize, what does this p of minus 1 mean? So p is a partition. So let's say something like p is 1 plus 1 plus 2. And then this is a fact from Python, is that if you have a string and you want the very last element, you do p of minus 1. And so in this case, it returns 2. P of minus 2 will return this plus symbol. So that's just a cute trick in Python. And again, SageMath is built on Python, so that carries over SageMath. Okay, so that's all I wanted to say. Then when we include, let me run this line again, and then type partitions of 4, then I get the correct answer.